In this video, I will demonstrate a simple logic circuit design using basic gates and OR and NOT gates to perform a specific logical operation. The circuit uses 3 AND gates, 3 OR gates and 4 NOT gates. The AND gate output a high signal, which is 1 only when all of its inputs are high, otherwise the output is low. The OR gate output is high if at least one of the input is high. The NOT gate inverts the input signal. In this design, we have 4 inputs, A, B, C and D. As you can see here, for the first one, A bar and B bar is connected to AND gate, producing high output A bar B bar, while input C bar and D bar is connected to second AND gate, producing high output C bar D bar. The output of these 2 AND gates were then connected into another AND gate to produce final output, which is A bar, B bar, C bar, D bar. In this circuit, signal input A and B connected to one OR gate, giving A plus B, while C and D is connected to another OR gate, giving us C plus D. Both of these OR gates produce a high output 1. The resulting output of both OR gates is then connected to another OR gate to produce the final output, which is A plus B plus C plus D, where the high output will make the dialysis machine to give a warning signal. Moving on, here this circuit was originally designed using the basic gates, and we will now replace those gates with NAND gates to achieve the same or improve the functionality. In the original circuit, we use an AND gate that takes 2 inputs A and B and produce an output, and also C and D to produce an output that is 1 only when all the inputs are 1. However, a NAND gate is the inverse of an AND gate. It gives an output of 1 in all cases except when both inputs are 1. In this modified circuit, we replace the AND gate with combination of NAND gates. To implement an AND gate function using NAND gates in this circuit, we take the output of a NAND gate and feed it into a second NAND gate. This produces the equivalent of an AND operation. Similarly, in this circuit, to implement an OR gate with NAND gate, we use De Morgan's law, where an OR gate can be made by first inverting both inputs, then passing them through a NAND gate. This is equivalent to an OR gate. After that, we use quarters prime to stimulate this design, and the output of the NAND-based circuit matches the expected result of the original basic gate circuit. This demonstrates the versatility of NAND gates. By using only NAND gates, we can reproduce the same behavior as the original basic gate circuit, showing how NAND gates can function as universal gates in logic designs. Therefore, in this analysis, we have 2 circuits that produce identical waveform. One is based on an AND gate and the other uses NAND gates. In the original circuit, the AND gate produces an output normal that is high 1 only when all inputs are high. The waveform of this circuit shows a high output for normal when all inputs are high and a low output in all other cases. Meanwhile, OR gate will produce a high output, in this case a warning alarm from a machine, when either one of the input is high and low output for all other cases. When the output is low, no warning alarm is produced. We replace the AND gate with NAND gate. The NAND gate output low, which is 0 only when both inputs are high, which is the opposite of the AND gate. However, by feeding the output of the first NAND gate into a second NAND gate, we effectively invert the output, replacing the AND gate behavior. As a result, the waveform for the NAND gate circuit is identical to that of the original AND gate circuit. This confirms that NAND gates, being universal gates, can reproduce the same logical behavior as the original AND gate circuit. That's all from us. Thank you.